Awesome. So we're gonna pick up where we left off last week, which was right at the very end of stacks. So, as you remember from last week, there are two main properties of stacks. One that it is a first in last out data structure. That is, if you like have something that you put in really early on, then as you're popping stuff from the stack, you're gonna get it out like really late on. And the second is that they have push and pop functions. Right, so you can only really do two main things to a stack. Sure, you can have other stuff like size, or you could peek at the top element instead of removing it, but for the most part, you're really just looking at two main functions with regards to stacks. So last week we went through a couple of problems where we tried to implement a stack using a single linked list or array, and we also tried to balance brackets using stacks. And do y'all remember exactly how that solution went last time?
Yeah, so you like, or okay,
Yeah.
but you push onto a stack, and you left braces, and on a right brace, you pop off, and if it's the pair, then you know you're correct, and you keep going, and then you return it whether or not the queue or the stack was like empty at the end.
Yeah. So that's sort of how we would balance the brackets, and that's because stacks are really good at keeping a reverse order of elements on hand. So we're going to keep that in mind right now, that we want a reverse order of elements on hand. And today I'm going to add on another thing, and you're really going to see this next week when we go into like DFS and BFS with regards to trees. Stacks are a really good way of removing like recursive behavior within your program. If you remember, all recursive calls take up stack space. So you can think of it sort of as, well, when I explicitly declare a stack, I don't need to really use that recursive stack anymore. And you're going to see what we're talking about with this next problem, which is honestly pretty hard, but I think is a really good example of like how stacks can be used in some very surprising ways. So before that, though, I just have an announcement to make, and that's that before we had all of our code in like these like zipped up archives on our website, and you could download them and run them locally, and it would be fine. But the thing is, we wanted you to be able to actually use the tools of the industry and sort of see how our code changes over time, which is why now we've put all of our code that used to be up on our website into our GitHub instead. So all of the links on the website still work. They just lead to the GitHub now. So all of the past solutions are now posted there. And I think it's really nice because this allows for the class to be more collaborative too. If you want to, you can submit your own solutions via pull request. And that way you can sort of work together collaboratively to get towards the best solution. You can ask like questions, open issues, all that good stuff. So later today, we're going to be looking a bit more at it. If you want to right now, it's up already on the course website, so just feel free to peruse it as you may. So let's talk about a prefix calculator then. So do any of y'all know what prefix notation is? I mean, it says it right there, but do y'all have any experience with it? Okay, so normally when we do math, we use infix notation, right? So in infix, we have like our operators in between our operands. So if we had 5 plus 3, then the plus would be in between 5 and 3. In prefix, you have the operand before that. So it looks like plus 5, 3. And like you can nest them together like in the example up there. Instead of like the quantity 6 minus 2 times 9, then you'd have times, parentheses, minus 6, 2, close parentheses, and then a 9. So this might seem sort of similar to something that you may have seen depending on who you took discrete math with. No, okay. All right, cool. So this is pretty similar to the way that a lot of functional programming languages are set up. And you're going to see why in just a little bit. So do we have any questions on what prefix notation is? Seems pretty simple, right? So say that I give you a prefix notation math expression, like the ones that we have up here, and I'm going to give you like something containing either positive or negative integers, and I just want you to make a 4-function calculator with that, with division rounding down as regular integer division happens. So a couple of important assumptions behind this, right? We're going to assume that everything is space separated. So if we wanted to separate this expression into its individual tokens, like for example, a number or an operator or like an open or a close parentheses, we'd be able to do so pretty easily. You'd assume that all of these brackets are correctly balanced, that the syntax is correct, so that way we don't have to use this thing from last week to actually make sure that our brackets are like balanced. And we just also won't have to worry about like, integer overflow. We don't have to worry about like dividing by 0 or like integer overflow or anything like that. Just trust that the expression is a valid mathematical expression. So given that we're on the stacks unit, how do you think we might be able to do that? Or even without stacks, like how might we want to do it, like if you just looked at it maybe recursively?
If you think about it recursively, especially for this problem right there, you could say like I have a multiplication, so I'm looking for 2 more things, and the first one is an expression, so you recursively call multiplication on that expression, and then the next number that you're expecting. Or if that's also a bracket, recursively call. So I guess you don't even have to, you can just recursively call your function on your 2 inputs every single time.
Okay, yeah, sure. So like that sounds good, right? I think one of the hard parts of that is like trying to figure out the bounds of like what this actually is. So you take a look at this and you'd say, okay, well, I'm going to try to evaluate this expression. There's another expression inside of it, so I'm going to recursively call this like calculator on whatever expression is inside of it, return that, and then feed the return back into the outer expression. If you have a ton of nested expressions, I think this gets a little bit tricky if you do it that way. In a lot of cases, because like you have so many like opening and closing brackets that your code can get a little bit messy. Recursion definitely is a pretty good idea, though. But let's think about what you said a little bit more right there, right? You said, okay, well, if you see another like nested expression, right, you'd want to go to the next level deeper and call it on that. If you have something nested, how might you be able to use a stack? Especially considering that stacks keep a reverse order of things on hand. And honestly, like take your time to think. There's relatively few questions today, because these questions are getting to be a lot harder. They're getting to be like more challenging, like maybe like more on-site type problems. And you're not expected to get this like anywhere close to immediately. Yeah.
So this might be a dumb question, but in Python are stacks lists?
Yeah, sure. So you can implement a stack using a list by just having like your push function be like, append item to the beginning of the list, and your pop be like, remove the item at the beginning of your list. I'm not actually sure how lists are implemented in Python. I think they do implement it using some sort of a linked list thing, but don't quote me on that. And last week we did go over how you could implement a stack using a linked list. So if you want to, you could like definitely look at those for review. But for now, stacks are, like we talked about last week, right? Stacks are an abstract data type. You can implement them in a ton of ways. And for now, you don't even really have to worry about the ideal behavior for push and pop. As long as you're able to get the first in, last out sort of functionality of a stack, that suffices for this problem. We're assuming that these expressions are not so complicated that you need O of 1 for all of them.
I guess one thing you could do is if you read it reversely, right, and you put for the example you put, and you could treat brackets as their own expression.
Yeah.
Right. So you pop in, you push 9 and then you push in the brackets for the subtraction with 6 and 2,
Uh-huh.
and then you'd also push in the star. And then once you're done reading the expression backwards, you start popping. And if it's an operator, you pop the next 2 and recursively call the function if you need to, like on the -6 2, and evaluate with that. That's
Okay. Yeah, sure. So what you're saying is let's push all of these things in and then take a look at the operators as you pop them back out.
yeah.
So how would wouldn't the operator sort of get buried like a little bit deep in the stack?
Well, if you push the 9 on first, like you read in backwards.
Oh,
So like
okay,
you
I
push
see.
in the 9 and you push in the brackets as
Okay.
one thing, right?
Gotcha.
And
Yeah.
then you also take in the multiplication, and
Uh-huh.
then you pop off. If it's an operator, you just treat it as an operator. If it's not an operator, you run your function on like a set of brackets if it has them.
Uh-huh.
Right? And so then that will return something. This -6 2 will return something. And
Uh-huh.
you also have the 9 because it's just a 9.
Okay.
And you can multiply because you know what you did before. That makes sense.
Yeah, sure. So I like that approach. I think that it's okay. So you would like push a 9, push a 2, push a 6.
You would push the entire phrase as something, like -6
Okay.
2.
Okay, so you push a 9. How would you know to push like a -6 2?
Like by brackets. Are you guaranteed that expressions have brackets around them?
Yeah, you do.
Okay, so you could push the entire bracket as like something.
Okay. So, oh, okay. I sort of see what you're saying. So you'd push so you'd have a stack of like an assortment of items, right?
Yeah.
You could have like a number or an expression. And if you see an expression, then you'd say, okay, let me evaluate that expression first, and we'll have a separate call stack frame with recursion. And once we finish that evaluation, we will return that and then continue on. So this seems good. I think that like this isn't as different from your first solution as you
It's pretty
would
simple.
think though. Yeah, it's like it's literally just pushing it in a different direction.
Yeah.
So I do you have a question?
No, I was just gonna say that like I would have done this recursion, I think.
Uh-huh.
But I don't really know how to do it so much with stack. Like my implementation was like kind of the same.
Okay.
Like I was gonna look at like find the brackets, like keep account of how many brackets there are to the left, and until you get to as many as there are on the right, like that's all the same bracket.
Uh-huh.
And then the first symbol is gonna tell you what to do to the thing inside.
Okay. So I think that's I think that in many cases it would be easier to like do it to think about it recursively, right?
Okay, maybe this is easier. Okay, so if you just push in everything reverse order, so you push in the 9, you push in the 2, push in the 6, and then you try to push in an operator, and you're like, oh wait, I have an operator, and then you pop off the next 2, evaluate that operator, and then push the result back on. So you like remove all recursive calls.
Yeah, that seems to work, right? That seems like a decent idea. So let's think about whether it would work with a bit of a more complicated thing.
Yeah.
So let's take a look at, say, if we had like if we had multiple expressions, right? So it's like plus 1, 2, and then you had times, and then you had times 5 plus 3, 4. So what do we think the result of this is, right? If we were to evaluate this like inside out as we would normally, it would end up being so over here this would end up being a 7. Let me just copy this over. So this would end up being a 7. This would end up being a 35. This would end up being a 3. And so overall this would end up being a 105. So that's the end result that we want to get to. So Simran, your strategy would be to walk backwards from the very end and say, okay, let's take a look at 4, push 3, you see a plus, and you're like, okay, I'm going to pop the last two, I'm going to add them, I'm going to push them back on the stack. So now my stack is going to, so you had a 4 and a 3, and then you pop both of them, now you have a 7. And then now you have a 5, and then now you multiply them together, so you have a 35. And then now you have a 2 and a 1, and then you go to the plus, and you say, wait, that's a 3. And now you take a look at your multiplication sign, and you're like, okay, awesome, that's a 105. So that seems to work, right? That seems to work really, really well. So I just want to have you think about what might happen if I were like, wait, let's try to have like more than one operand, like so, or more than two like operands for each operator. Like so, say that I were able to do like 1, 2, and then -2 over here, then this would become like a 1 over here, and then you end up getting a 35 over here. Yeah.
Could you implement something where it counts up the number of terms in the bracket and then pops that, or like pushes, or goes back that many and applies that many onto the onto the operand?
Yeah, sure. So that, let's think about how that might work, right? So let's say that we have a count. In that case, we go 4. So we'd be like, okay, we're in this enclosure right now, and we found 2 items, and we found an operand. So let's pop 2, and let's do whatever we want with those like 2 operators. Oh, with those 2 operands, and then after that, we're like, wait, how many are we at here?
We're at 2.
We're at 2 again. How do we know that?
Because you've pushed both of those off and then popped a 7 on. So it should be a 7 and then a 5, and then those 2 are both on.
Mm-hmm. Yeah. So what happens if we had like a 6 over here, right? Then you'd need a separate scoping you need like a separate count for like every single scoping that you had.
Did you know with another stack or no? Could you?
What did you say right there?
If you could keep track of your counting with another stack.
Yeah, so that does seem reasonable, right? Like you pop your counts onto like a count stack. But then like what you would have to do is you'd say, okay, well, when I reach another enclosure over here, I'm going to push a 0 on. And then for every item that I see inside the stack, I'm going to add 1. And then when I finally have an operator, I'm going to like, do my stuff with it, like return the actual result, and then pop whatever it is off of the count stack. And then whatever's under here, I would just continue incrementing as I like went through. So with the additional care of saying, oh wait, I need to increment whatever was underneath by 1, because this is another count. Okay, so that also seems pretty valid. Let's actually try to see if that. Okay, that seems very valid. Yeah. Let's go through and let's try to see if we can code this then. So for now, let's only worry about sums and products, because I feel like if we were to add on like division and division and subtraction, in many cases it's like largely the same thing, right? So let's have a stack of integers called counts, and let's have a stack of integers called results. Okay, so eventually what we want to do is we want to take a like we want to take a look at this, and after everything is through, what should we return? If we're continually pushing the result of it to the stack again, then eventually we should try to just pop the last item off the stack, right? So return results.pop. Okay, cool. So now let's go through and let's split this string into like an array of its tokens. So like that. So then afterwards, we're going to say, okay, let's have an index and let's iterate through backwards through the array, right? So let's have a for in i's tokens.length -1, I is greater than or equal to 0. Let's say okay, so we have a couple of things that we can do, right? So what are our options? What are our cases? So let's just think of it in terms of like maybe a bit of pseudocode right now, right? So we have a couple of cases where it's like you could have a closing parentheses, in which case you would push a 0 onto count stack, right? You'd have an opening parentheses, in which case you would apply the operator and push it back to the stack. You'd increment, you'd pop the current count, and you'd add 1 to the count below it. If you had a number, you'd push the number to the stack, and if you had an operator, then what would you do?
You pop the count number from the results.
Okay.
Number.
Yeah. Okay, so it looks like we're guaranteed that our operator is always followed by this opening bracket, right? If we're going through it in reverse order. So we only need to define one of like either of these. In that case, it might be easier to just apply that operator once you see the operator, and then if you see an opening parentheses, just ignore it. Right? Seems pretty fair. Okay, cool. So let's copy this over and see. Okay. Oops. Let's put this here and just try to use this as our guide for the next several minutes. Okay, so then we'd say if token.equals this, then counts.push 0. Else if token.isNumber. I don't think there's actually an isNumber thing in Java. And I think that like if you try to use integer.parseInt on something that isn't a number, it like just throws an exception. But I think we can actually use that to our advantage by writing our own Boolean function for like isNumber. So we can write a we literally just try to push, we try to cast it to a number. And if that works, return true. Otherwise, you go to the catch block and return false. So in an interview, this is what I would do. When you're actually, I would probably make a note that like, I would do something that doesn't require like try catch blocks, because exceptions should be for exceptional circumstances, not for very ordinary circumstances where like about half of your tokens should not be numbers. But we can say for now this should be good enough. So else if isNumber token, then let's do results.push register.parse int token. Okay, so else if, okay, so this thing we have the ignore, so we don't do anything. So all we need to do now is to worry about like our addition and multiplication cases. So let's take a look at else if token equals that, and we're going to probably be able to refactor this into something cleaner in a little bit, but for now let's just do this. So we have our multiplication and our addition methods, right? So when we add a different number, then not only do we need to push the results to the stack, we also need to increment our count stack, right? So we do counts.push counts.pop plus 1. And that's just incrementing what was like directly underneath it. So if this token is equal to that, then what do? We say that the first result, so we're just going to call it temp because I'm not feeling super creative today, but we're just going to do results.pop, and then we're going to say for an I is 0, I is less than counts.pop, I increasing, except we already have a bug already, and it's not just the fact that we reused I. Why is this not great?
The for loop?
Yeah.
Wait, also aren't you supposed to pop off the results? Wait. Shouldn't you have a count that you take from the counts and then pop off the results?
Pop off that many results.
Yeah.
Right.
Pop off that many results.
Yeah. So like we're gonna do that like inside here, but I'm just asking why is this line going to fail?
Oh, I'm pretty sure it's gonna rerun counts.pop.
Yeah, it's gonna rerun counts.pop every single time. This has bitten me like a lot of times when I forget that inside that for loop, like that's basically like just writing like a while loop where like that stuff, whatever is here, evaluates every single time, which is not great. So let's have an int count is equal to counts.pop, right? So why do we still need to pop it a first time though?
From the counts or from results?
From results. So, or theoretically, like we could just have int temp is 1, and then just say like temp times equals counts.pop or results.pop, right?
You'd probably end up missing one of the numbers, I'm guessing.
You'd end up missing one of the numbers. Yeah, so if we, like, so the thing that I was trying to get at is, a lot of times, like, you'll try to use the same temporary variable for both addition and multiplication, and that doesn't work, right? Because you need to, so that doesn't work because you need to, if you have temp as 0 for multiplication, you're only ever going to get 0. So it's just like one of those small things, but it's something that I see pretty often with this problem. How are we doing on the camera? Yeah. Okay, so while that's happening, let's just say temp is equal to results.pop. So this is applying the operator, and then we do results.push temp, and then we pop the current count. So that's already happened. We did that, but we need to remember to increment the count right below it. So counts.push counts.pop plus 1. So very similar code over here, except that we're going to be doing it with addition this time. So in this case, temp is 0, and temp plus equals that. So that seems to be pretty good, right? Let's see if we can test it out on one of these. So do we see any glaring errors in our code as of right now? I think that's pretty good, right? I don't see anything that would cause immediate failure. And in many cases, like when you're in an interview setting, like you would want to just get through with it and just test it out, right? So let's try testing it out. Let's try running this. And we get an exception, an array out of bounds exception. So why is that? It's because over here, we're incrementing instead of decrementing. Okay, so aside from those, what do we see? We have an empty stack exception where we tried to go over here at line 36, and we have nothing to pop. So we should initialize what we have over here by having a count as a 0, right? So counts.push 0. That's the way that we're always doing it, because you need to have like an initial count at the very bottom for it. So let's try this one more time.
Wait, but shouldn't it do that if your entire expression has a parentheses on it already?
So did I miswrite this expression? Interesting. Okay, so yeah, that's interesting, right? Because it seems like we should have already pushed a 0 over here. So let's think about what else might be causing this problem. We know that the issue is when we got to the multiplication sign, which is at the very right-hand side over here. And I think that it would help if at every single point over here, we sort of printed off what our stack actually contained. So let's okay, so over here, with our, times 2, 4, 5, we have a count of 1 and a 5, and then we have a count of 1 and a count of 0 and a 5, and then we have a count of 1 and a count of 1 and a 4, and then we have a count of 1 and a count of 2 with 5, 4, 2, and then we just have a count of 2 because this is 6, and then we have a count of 2 with that. And over here, it just looks like we counts.push. Okay, so line 36 is forever here. So at this point, it didn't want to pop. What do y'all think is causing that?
Wait, do we need to? What are you pushing counts on multiplication and addition? We don't need to push back, do we?
I think we do, right? Because that's what we're saying is we finished this sub problem, and we now have an additional operand over here. So that seems to make sense, right? Counts.push, counts.pop, that's 1. Let's try to see if we can run it on something a bit simpler, right? So let's just try to do it on like times 1, 2, 4, and see if that still fails. At that point, we end up in an issue at the exact same place. Same thing with a +2, 4. See if we get that same issue. Yeah. So in that case, we have that we get to the operator, and we say, okay, let's just move what our print statements are to a little bit above right there. So let's remove this and see what we have. So we have let's not even worry about results. Let's just worry about counts. We get into an issue at, oh, okay, because we changed it to a plus. Let's change this back to a multiplication. So over here, our counts is already empty. And what we can say with that is we can just add an additional if statement, right? So like if you're at the very end of it, then you won't have anything underneath. On the other hand, what you could do is you could just have a dummy variable over here and just do counts.push 0, and I'm pretty sure that would take care of the issues that we're seeing. Yeah, so that indeed took care of the issues that we're seeing. And I think that it's easier to write that than to write an additional if statement over here. Just like we saw with the dummy head in our linked list, sometimes you'd want like a dummy thing at the bottom of your stack, depending on how you wrote it. So this is pretty good. Let's test it to make sure that it works on like different amounts of numbers. So let's say that this thing plus 2, 4 times 5, 2. So this would be 60. And let's just make sure that the result on the right is actually 60. Yeah, that's 60. So that's perfect. This is one way to do it. Right now, I'm going to actually show you another way to do it that I think is also equally as valid. So this is something that I prepared beforehand, and it works largely the same way. And I'm just going to put this inside calculate for overall, in where it also includes being able to deal with like division and subtraction. So the difference between here is that instead of having a stack of the results and the counts for how long each individual bracket is, instead I have something that is a stack of operators and a stack of the results. So I iterate through it forwards, and every single time that I come to an operator, I push something onto the operator stack. And then this works for only 2 numbers right now, but with a really quick change, I can change it such that it would work with any number of operators. And the way that it would work then is it would, hold on. So over here, you would push the operators, and then you would pop them off, and it would just work pretty much the same way, except that it would go forward instead of backwards. So one of the advantages of doing it this way is that with this sort of calculate, you can actually do something regardless of where the operator is inside of your expression. Like, you would still be able to have something valid. So over here, you can see that even if we have something that's just infix notation, like 2 plus 4 times 4 times 3, if you did calculate over here, hold on. If is, it's called is number. Okay, cool. So over here, you'll see that even though this is infix notation, that is like the normal way that we do things, you're still able to get 6 times 12 and get the right answer over there. So I did this before class when I didn't have time to like make this extensible to all different sorts of numbers. But hopefully this just sort of like expanded your view of what actually is possible with stacks. And so we've already done calculate arbitrary length clauses. That's great. When it comes to dealing with division and multiplication, it's literally just adding on more of these, right? So over here, I just want you to think of, how we might be able to refactor the code such that it's more, such that it's cleaner. And this is going to be the last thing that we do before we take a short break. So if you'll notice, there's a ton of code right here. Most of which is entirely just a repeat of what's above. Yeah.
Just define another function that has that functionality, where you input TMP.
Yeah, sure. So the way that I would probably do it is I'd have a set that I would call operators, and I'd say if the string, like if your operator set contains this token, then run it with the token. And then within that other function, you'd have like just a bunch of like if-else statements. So that's what I do over here, right? So set of string operator is a new set, and then I just do operators dot add. What do we have? Plus, minus, divide, and multiplication. All right, cool. So dot add. Can we actually do that? Like,
it's gotta be a collection.
It's got to be a collection. Okay, cool.
But you could just make that an array right there. Right?
Yeah. So for string t in
Well, no,
that,
you can add the array into the set.
you wait, is an array technically a collection?
Oh, an array list.
Yeah, I don't think an array is technically a collection. So it's kind of annoying, but this is the Java way. Okay, dot add t. All right, cool. So now that we have our Ed Sheeran discography set up, and let's go over and let's try to refactor this, right? So let's say over here, else if operators dot contains token. Let's do like, what should we call it? Let's do execute token. Okay, so execute operator of the token. So we need to take care that we have everything that we need, right? We need both counts and we need results. So let's give all of that. So token, count, and results.
What are your thoughts on using like private instance variables in like interview questions so you don't have to keep asking stuff?
Private instance variables. So I'm not a fan here specifically because right now, if you'll notice, calculate is a it's like a static function. So yeah, that would probably be a bad idea. But I would talk this over with your interviewer. If you were to like make an instance of a calculator, that would be fine. I think that a calculator usually seems more like a utility though, which means that I would more often call it as like a static function. So yeah, over here, let's do private static void execute operator. Execute operator. And what are the parameters? It's a string token, a stack of string integer counts, and a stack of integer results. Okay, cool. So then I think that we can honestly just copy this over and see how we might be able to tweak it depending on what it is. So let's remove this part. We can say that int temp starts off as 0, and then we can say if token equals, what do we need in terms of actual like, so what do we need in terms of like temporary variables which are not 0? Subtraction seems fine. how would subtraction and division work? So with two things, you would just say, okay, I'm going to pop off the first one, I'm going to pop off the second one, and I'm going to return whatever it is that's the first one, minus whatever it is that's the second one. How do you define subtraction where it's like a lot of things? Like if you had like minus and then like 555, what does that mean?
Okay, it's negative. Well,
For the time being, let's sort of just assume that it's like, you know, for the time being, let's assume that it would just be, it's whatever the first thing is minus everything else. So then what does that mean with division then, right? So that's like really like weirdly defined.
the first one divided with the second one, then the third thing divides that. I guess. That means
And the third thing divides that. So, okay, that seems to make sense. So let's, okay, that seems to be pretty consistent. So then the ones where we would need to have the first thing not be 0 to either multiply or divide by are going to be addition or multiplication and division, right? So if token's that or token is a divide sign, then increment temp to be 1. Okay, so count equals counts.pop. I think that might be better instead of having this temp thing to instead just be like, okay, wait. So what are our special cases? Addition, totally fine with having temp as 0. Then multiplication, you need temp to be 1. For division, you need temp to be the first item. And for subtraction, you also need for temp to be the first item. So it seems like temp has so many things that we might as well just split it up into a bunch of different if statements, right? So temp starts off as 0, but if it's multiplication, then temp becomes 1. Else if token equals division, then
well, actually, couldn't you make temp always be the first number? Because like if you're adding, you're just adding 0. If you're multiplying, you're just multiplying by 1.
so how would we have to change this then? Our counts would just have to be counts.pop minus 1, right?
Like the
Yeah,
for loop?
that
Yeah.
seems, okay, so I was getting there. That seems
Oh.
like the simplest way
Okay.
for you to write it, right? Like, you could have like a case switch statement, but eventually we're going to get to the point where we're like trying to like define our own operations, and then it becomes impossible. So let's just have temp be results.pop, right? And then so over here, then we basically just have a switch statement. So if token that, else if token equals.
Is it overkill to like? I think it's the same thing. Passing lambdas. But like,
So I'm actually not entirely sure how lambdas work in Java. Honestly, this thing works a lot easier in a language like Python,
okay.
where lambdas are a lot more like just a natural part of the language.
Yeah.
But for now, I think this should be fine. So then we have else if that, and then finally else this. So we have, let's just do plus, multiply, subtract, and then finally divide, right? So temp plus equals that times subtract divide And after all of that, you push that in. And let's, for now, not delete this. Let's just comment it out and see if this makes sense. So after we give all of that, let's do calculate. I know it says only sums and products, but we've changed it a little bit since then. Let's do what we had over here, this function, right? And we said that it would be 35. So, moment of truth. 420.
I think that might actually still be right. Did we change this?
Okay, so we wait. So this is 7 times 420. Yeah, that's correct. Okay, so let's say that instead of this being multiplication, let's hold up. So subtract 1, 2, and like 4. So this should end up being -5 times 420. So that's like, what, -2100. So let's see if this ends up doing what we want. And we got 8. Is that?
That's the first one. Oh, we got 8.
No, yeah, I got 8 again. Okay, so let's see if we did anything that's just a little bit not right here, right? So just making sure that everything over here is calculate only sums and products. We do have plus equals, times equals, minus equals, divide equals. Okay, so let's just try to see if we can simplify this a little bit, right? So let's just see what it thinks -124 actually is. I think that might be a part of the confusion. So it thinks that that's correct. That's -5. And let's just see if it thinks that the other expression is what it is in this. And it thinks that that is 5. So that's interesting. I don't think we broke any of the very basic functionalities that we had. But, okay, so it thinks that this is 7. So that just means that it thinks that 7 times 5 is 5. And let's try to see if we can just only worry about this thing. So string single test is string array that literally just has this one thing. And let's just print out what happens with all of these. So counts and results. Okay, so then over here we have counts being, so counts are 0 and 0, and results is 4, which that sort of makes sense. The only thing that we have is 4 and then 3. And then, okay, so this is after we have already popped it out. So let's put this beforehand, so that way we actually know what happens before we're about to like pop it. And at that point we have 0, 0, and 2. So it thinks that there is nothing in here. Adds that. And on the stack is 4 and 3, and eventually that gets off. And let's print it out afterwards too, just so that we see what happens after the expression is evaluated. It seems odd because this means that the execute operator thing only ever actually happens once. Doesn't it? Because we've only ever printed out this thing once, which means the last operator isn't actually executing. Yeah, so at that point we have 7 on the stack. And over here, it just seems like oh, it's because I didn't put a space in between this. So, okay. All right. Cool. Okay, so then after all of that, we should be able to, so this does think that's 35, so then we go to tester, and everything should be working as expected. So I guess the assumptions that the input would actually be valid are actually some pretty tight assumptions, because this thing just dies when it doesn't work. Okay, so even though that is the case, it still appears as if the very last one isn't working. So this thinks that's -5, that's true. This thinks that's 35. This thinks that's 7. And the very last one still thinks that's 8. So something is... Oh. Okay. Wow. -175? Does that work?
I think that makes sense. 35 times 5.
35 times -5. Yeah, awesome. Okay, so I'm going to clean this code up a little bit, and y'all can take a look at it after class, but this is luckily all that we have to think about for this calculator, because I'm sure that y'all are tired as of right now. Okay, so let's take a bit of a break, and we're going to come back and actually do doubly linked lists and queues. So welcome back, everyone. So we're going to go over a bit more about what queues are now. But before that, I'm going to talk to you a little bit more about how like next steps might have looked like for this calculator, right? So we already did the first step, which is generalize it to like multiple operands. We didn't have time, but after that we could have added variable binding. In a very simple case, like for global variables, you could have added just like a hash map and then made your methods non-static. So that time you could like define something, and it would work a lot like, you know, a regular TI-84 calculator would now. You'd be able to do a bunch of functions, and you'd be able to save local variables. So then after that, it's a bit more of a stretch, but you can add conditional statements and function declarations and support for other data types and evaluating multiple expressions in succession. And if you manage to do that in a 1-hour interview, you're a god, because you will have made a fully functional Lisp interpreter. So it's really interesting because this is actually the final project for Berkeley's equivalent of Comp Sci 101, which I think is really cool because, I mean, you took Comp Sci 101 here, right, Kunal?
I took EJR 103.
Oh, you took EJR 103. Okay, like, EJR 103 doesn't really have you do, like, that many, like, what you would consider, like holy crap projects, right? Like, the way that if you built a fully functional interpreter for another language in your first ever Comp Sci class, I think that would be, like, just like a mind-blown moment. So if you have more interest in that, then feel free to take a look at it online. The link's in the PowerPoint. The PowerPoint's online. So let's talk a bit more about queues. So queues are sort of the opposite of stacks. Whereas stacks were first in, last out, queues are first in, first out. So it's sort of like a checkout line, right? If you line up first, you're going to get to the cashier first. You're going to get out first. So this is really useful for tasks where you need to keep a like straight order of elements. So stacks were reverse order, queue is like going forward order. So just like stacks have a push and a pop method, queues have add and remove methods, and these are largely like, you know, analogous. Both of them have to run in constant time. And they can have more methods like taking a peek at the top element or having the size, but these two are fundamental. And just like stacks, queues are abstract data types, so there's more than one way to implement a queue. We're going to go a little bit out of order because right now we were supposed to implement a. Oh wait, actually, no, we're going to go exactly in order. We're going to implement stacks using queues. So you can have any number of stacks or any number of queues that you want, and you want to be able to implement a stack using it. So you might not be able to get O of one runtime for both push and pop. You probably won't. Like it just seems like they're two entirely like opposite data structures in terms of their goals. But you should be able to talk intelligently about like the trade-offs that you make when you're trying to design this. So this is where we go to our new format and we take a look at the GitHub. So let's form into teams and let's try to take a look at stack versus stack using Q1 and see what we can improve. So let's reconvene on that in like 5 or so minutes and let's see how that can be improved. If y'all want to talk it over, that would be ideal.
What website is
This is docatalyst.co/interviewprep. So at the very bottom, not the very bottom, but you'll see a thing that says solutions under linked list stacks queues 2. You can, wait, did I not merge that pull request? Oh, no, okay, you just need to go solutions. Okay, so just go to solutions for linked list stacks queues 1, and then go one folder up to S17 and go to LLSQ2. So then take a look at stack using Q1. Let's see what you think of this.
LLSQ1?
LLSQ2. And you can find stack using Q.java. So whenever y'all have an idea of what you think this is doing with like what the main idea of this implementation is, let me know. It might help if you draw out a diagram.
I kind of think I know.
Yeah, sure, Kanal, what do we think?
Is it adding to, like, it's adding to main and then, like, kind of flipping it onto alt and then flipping it back onto main? Or...
Yeah, so over here in line 31, it seems like every single time we just redefine what main is, right? And so whatever the alt is, you add everything on there, and then you shove everything that wasn't main on top of the alt, and you say this is the new main. So that seems like a pretty decent idea, right? If you continually do that, then whatever's at like the front of the queue, which we'll visualize as the bottom, will get removed first, right? So just like how if you push something onto a stack, whatever's on top gets removed first. If you push something into a queue and that thing's on the very bottom, that thing's going to get removed first. So at least functionality seems to be correct, right? So what are the trade-offs here? What's fast and what's slow with this?
Everything but push seems to be fine, I guess.
Yeah. So it seems like pop, empty, and top are all O of 1 operations. But it seems like with push, you need to push everything and like re-push everything inside, right? So what might this be good for? Like what situations might this be good for?
Might already have a list and you just want to pop things off.
Yeah, sure. If you already have like a lot of things and you just want to pop things off. I was thinking like if you're not pushing very often, but you are like peaking at the top very often, then that might make sense. Like if you constantly just have to check like, yo, is my current thing valid with whatever was most recently pushed to our stack, quote unquote. So that seems pretty decent. But it seems like this code, while it is like sort of straightforward in terms of thinking, like defining like main and alt, are those really necessary? Because you already have like stacks like 1 and 2, right? They don't have any like extra space necessarily because these are just pointers to like existing things. But you can think of possibly some ways to clean up this code, right? How might we be able to clean up this code?
So I mean, if I was doing this in Python, then I would use like insert instead of push. So that inserts it at the bottom. So do like insert 0 and whatever you want to do.
Yeah.
And then your pop you would make as pop 0 and like you would pop at the first thing.
Okay, that's fair. So I was thinking more like there's nothing that's wrong with this. But there are two improvements. The first one is something that's stylistic, and the second one is something that can actually reduce. So I guess both of them are technically stylistic. The amount of storage is the same regardless of like what method you're using. But you can reduce the number of extraneous variables that you use in various ways here. And let's try to think of how we might be able to go about doing that. So we already said that like main and alt aren't really necessary, right? Because we already defined like Q1 and Q2. So how might we be able to change that?
I mean, like you can just use Q1 and Q2 instead of using main.
Yeah. How can we? So how would you suggest that we like refactor this?
This whole like if else, if Q1 main,
Uh-huh.
I'd probably make that like yeah, you could make it. Well, you could definitely do it by using only one where you store like you make Q1 equals Q3 and then put Q3 or Q1 onto Q2.
Uh-huh.
Or other way around, you put Q2 on Q1 and then Q3 onto Q2. So instead of
Okay, yeah, right. So you can just swap it. In Python, it would be even simpler, right? You'd just be like A comma B equals B comma A, and then that would just be an instant swap. So take a look at stack using Q2 and see if that's similar to what you're doing. Oh, whoops. 20 is supposed to have an additional line there that says swap. It is basically like what you're doing, right? You're doing the exact same swap sort of thing that we're talking about, and we just always use by convention Q1 as the main one. So one last thing that we might want to think about is, do we need 2 queues? So basically we're saying we have 2 queues, right? One left and one on the right. This one's our alt, and we push something in there. and then we just like shove everything that's in Q1 on top of it. And then we say, okay, now this one's the main, and we have an empty one as the alt.
And like you could always just add to the first one.
How might that work?
I mean, like I said, like I don't like in Python you just like you add or instead of using fn, you should add you use insert with the 0.
Yeah.
And that already fn's to the first.
Okay. So, Simran, do you have any thoughts on this?
So I guess you could remember the size and do something like that. Maybe a little.
No, I think you're on the right track. Yeah. No worries.
Oh yeah, if you know the size, you can just remove the size -1, and then the last one is the one that you want to pop.
Yeah, you just keep like you basically just like sort of cycle the queue through itself, right?
Yeah.
And let's take a look at stack using Q3 and see what they're doing here, right? That line right there, that's where the magic happens. You keep track of the old size, and then you just say, all right, every single time, I'm just going to add what I just removed. And that just sort of takes the stuff at the bottom, pushes it back in the top. So that way, even if your new item was at the top first, you cycle through it that many times, and eventually it gets buried underneath everything, and it's ready to be removed at the bottom if you were to pop it. So, yeah, what do you think of this style? Would you prefer me having like these like multiple snapshots of like incrementally improving code to like writing out code myself? What do we think?
I think it depends on the problem.
Depends on the problem.
Because like this problem
Yeah.
sort of makes sense.
Yeah, this problem sort of makes sense. I think if we try to do it with Prefix Calculator, I think everyone would just be super confused,
Yeah,
honestly.
that would make more
Like, I confused myself at some points in the process of doing it. Okay, cool. So, I mean, again, like, I am really interested in education. Like, that's one of the main reasons why I am doing this. So, if there's anything that you think would be good or whatever, like that, that's my jam. Okay, awesome. So, we did the code quality drill. Let's take a slight break right now, actually. All right, cool. So now let's talk about doubly linked lists. So last week we talked about singly linked lists. Doubly linked lists are pretty much exactly the same. They have a data pointer and a next pointer, but they also have a previous pointer. And this makes it really useful because if you remember, one of the things that I said about singly linked lists is that once you like traverse past your existing head, you couldn't know what was before it. But with a doubly linked list, you definitely can, and you can traverse backwards. So there's a couple of assumptions when it comes to traversing backwards because backwards traversal actually makes it a bit more complicated. So the first one is that doubly linked lists will be valid. That means that for any two nodes A and B in the list, if A.next is B, then B.prev is A. So that way you don't have like this wonky stuff where if you traverse forward, you go this way, but if you traverse backwards, you go another way. That would just be really confusing. For now, we assume that the lists are actually a linear list. So the other thing is access, right? Because the entire list, because you can traverse forwards and backwards, you can see the entire list from any node. So it's kind of confusing when you say this is the head. But by convention, we're going to say that like the head pointer is a head pointer that has a null previous pointer, and the tail pointer is a pointer that has a null next pointer. You'll also see things like circularly linked lists where the head and the tail are connected to each other. But in general, let's just use this convention when we're talking about this class. So if you'll notice, we've sprinkled these slides throughout that are just like, wait, like how's like A related to B related to C related to D? Well, right now, we're going to show how everything is related. How linked lists, stacks, and queues are all pretty much the same thing. And like even even arrays in terms of being able to convert one sort of data structure into another sort of data structure. We already implemented a stack using queues. We already implemented a stack using both an array and a singly linked list. It's really easy to implement a queue using stacks, as like sort of the opposite of the previous exercise. And right now we're going to go through implementing a queue using both a doubly linked list and an array. So I know that I sort of skimmed over the part about implementing a stack using a singly linked list and an array because I sort of wrote out the code in like table format before that. But with a queue, it's a little bit harder. I'm going to step through exactly what it looks like when you implement the queue. So, like before, we have dummies. Here we have a dummy head and we have a dummy tail, right? And just like in the array, we have a head pointer and a tail pointer. When you add something to the queue, you add it. So when you add something to the queue, you add it directly behind the dummy head, and likewise, you increment the head pointer and the tail pointer. And just like before, add something to right behind the dummy head, and then whenever your head increases, whenever you add something, you also have to increment the head pointer if you were to use an array format. Same thing. And then here's removal, right? So with removal, you say like dummy tail equals dummy tail.next. Well, there's a couple more things that you have to do, but basically you remove the node right before the dummy tail. And for the array implementation, you just increment the tail pointer. And so on and so forth. So let's talk about the implementation using a linked list first. So that looks like, just make a new class. Array queue impl. And we're just going to say that this thing implements queue. And so this is going to be really nice because first we're going to import all of Java's util. And so right now it's going to yell at me because it says that you need to declare certain abstract methods. And let's just implement all of these methods. Okay, so let's not make it implement queue, actually. I don't want to deal with all of this. Oh my gosh. Okay, so we're going to refactor this, and we're just going to call it an array queue. All right, okay, cool. And it's going to have a couple of methods. It's going to have an initializer. Okay, so we have an array queue, and just like that, we're also going to have a linked list queue. So with a linked list queue, we can do stuff that's really nice. Like we don't have to worry about a capacity. With an array, just like with this stack or with the array implementation of a stack, we had a maximum amount of space within that array, right? But with a linked list, you can make it as big as you want. So the way that I'm going to do it is very similar to the way that we saw in these slides. We're going to have a dummy head and a dummy tail. So I'm just going to define the constructor. And we're going to have some variables. So over here, we're going to define a node, right? So class node. And it's going to have a node prev, node next, and a node or an int val. So okay, cool. So we have the setup that we need, right? And now let's define some private instance variables. So we're going to have a dummy head. And we're going to initialize them in our constructors. So dummy head is a new node. Well, we're just going to say it has a value of 0. And dummy tail is a new node, also with a value of 0. And we're going to say dummy head.next equals dummy tail, and dummy tail prev is dummy head. Okay, cool. So this is the exact setup that we have over here, right? We had at the very beginning, of it all. So the arrow on the left side is a prev, the arrow on the right side is a next. Dummy head has no prev, and dummy tail has no next. Awesome. So let's think about what it means to add something to this queue, right? So what are the two methods that we need to define? We need to define a pop, and we need to add and a remove. So public void pop, public int pop, and we're going to have a public void add or remove add, and we're going to say an int val, right? So when we remove something, let's talk about add first, right? So adding is going to be just adding something, like we said, directly before the dummy head. So let's make a new node and say new node is a new node with this value, right? And we want to insert it right in between what dummy head is over here and what was previously the last thing before dummy head. So we want to go between dummy head and 3. So that means that we need to keep track of what dummy head dot next is. So node next is dummy head dot next. So now what we're going to say is we're going to sort of link these connections. And if you'll notice, there's 4 connections that need to be made whenever you insert a node. You need to change this node's next and prev, like your new node's next and prev, in addition to the next and prev of the 2 nodes that were right around you. So what does this look like? Well, we know that we want to insert it between next and dummy head, right? So that means that no node dot next is next, next dot prev is new node. Okay, so we've dealt with the away from the trailing end of this queue. Then let's say that dummy head dot next is new node, and new node dot prev is dummy head. At this point, you've dealt with the connections on the head, on the leading, like the head facing side of this connection. So you've added that. And what about the remove method? If you want to remove something, then you're removing something that's right at the tail, right? And just like before, there's 4 connections that you need to sort of cut when you're removing something from the tail. The new node itself and the connections that were like right before it. So in large ways, what you're going to see is that the code for add and remove are sort of mirror images of each other. So in this case, instead of creating a new node, we're going to call it toRemove, and this is going to be dummy tail.prev. So you need to do dummy tail.prev, and then you need to know whatever was before that too. So node prev is equal to toRemove.prev. Okay, now we get to the part of cutting all these connections, right? So an immediate thing that you can think about is I need to cut the connections for both of toRemove. The next and the prev both need to become null. So toRemove.next is null, just like its prev becomes null. Okay, we've dealt with 2 of the 4 connections. Now let's link up those 2 nodes that were around this node that we're removing, and we should be good. So that means that dummytail.prev is prev, and prev.next is dummytail. Okay, so how can we be sure that this works? At the very end of it, we return toRemove's value. Okay, cool. So, okay, let's think of ways to test this, right? And we could write something that like prints out the queue the entire time. But I think that in the interest of time, let's just make sure that it at least preserves the queue quality. So what that means is we're going to write a main method. Going to initialize a queue. And we're going to push some values into it. So q.add 1, q.add 2, q.add 3, q.add 4. And then while... So let's do one thing where we have a isEmpty method. So I think that is important because there's a really easy way to do this without even having to, like, add a size. It's probably useful to add a size so you know how many elements are in a queue. But if you didn't want to do that, what you could simply say is public void isEmpty. You could just say dummy head.next is dummy tail. So while queue is not empty,
Gonna return to
yeah. Okay. And then let's just print out q.pop, q.remove. Okay, and it should be the exact same order that we put this in. So let's try this. Let's run the linked list queue, see if you have any issues. Oh, it's building my entire project, so that's a bit annoying. But let's see if this build works. Yeah, and that's exactly what we want. Everything came out in the exact order that we have initially wanted it to. So let's copy this over and see what we can do with an array queue. We don't need a node. We're going to remove any references to a node. And what we're going to say is that we don't care about that array queue. We're just going to make an array. And it's going to be the size of that. We're going to have a tail pointer and a head pointer. And I'm going to say tail is -1 and head is -1 at this point. So we're also going to keep an internal thing where we're going to have an int size. And it's a bit confusing because we're going to call this size is 0. So again, we have our remove and add methods and our isEmpty methods. We're also going to add an isFull method because our array implementation actually has the issue of dealing with like being full. And in this case, like we're just going to, for the sake of simplicity, say that you would return size is equal to your data. Okay. It's equal to the data's length. Okay. So, all right. When we add something, then let's just deal with those right now. But what does it actually mean to add something, right? Like we said before, when we add something, we're shifting the head pointer up. Not only are we shifting the head pointer up, but think about what happens if the head pointer wraps around the other side of the array. Like, in our drawings, it looks like our thing creeps up, quote unquote, but like we want it so that it actually like more or less like, is able to effectively utilize the array. What that means is that if you ever run past the top, you'd probably want to like, give it a mod, right? So that way it would go back down underneath. So let's say that we would do head ++ and then head % equals data.length. That seems pretty fair. But before that, what we would do is we would before that, what we would do is we would say, or then after we increment the head pointer, we would say data at head is equal to val, and then we'd increase that size. So one thing that we can do as a precaution is we can say if is full, return. Probably want to throw an exception if you're writing production grade code, but for now we should be fine. So let's think about what it means to remove then, right? So removal seems like it would be like decrementing the head pointer, right? But remember that we have a tail pointer. And instead of like with the stack where we like, grew the stack up and then decreased it again, what you're actually doing here is you're saying, okay, I want to kick the tail out. So we're actually doing the exact same thing that we didn't add, but instead to the tail. So over here, we just flip all of these and we say tail, tail, and we don't worry about the value, and we just decrease the size. But before that, we would have an int val is equal to data at tail, and then return data, return val. Okay, awesome. So let's make an array queue of size 5.
Does that fail at the first remove? Because your tail's initialized at -1.
At the first remove.
Because it'll take data at -1.
Wait. Yeah. So, we could do this a couple of ways. So, at the first remove, you could also have the tail pointer point to what was directly before what you're about to remove. So, if you just swap these, then you could just return data at tail over here, and that would work. So that was a good catch right there. So over here, we have the queue, and let's try to build the array queue now. And it returns the exact same thing. So let's just try. You can throw a runtime exception with no worries. Let's see if like this actually does throw a runtime exception if we try to add too much stuff to it, which hopefully we should. Yeah, and we get a runtime exception. So that is very good. It's performing the way that we'd expect it to.
If you try to pop and then add another one, see if it wraps.
Yeah, so we can do q.remove and then q.add, let's call it 6. Right, so in that case we'd have 2, 3, 4, 5, 6. And that's exactly what we want. So, all right. In the last couple of minutes, we're going to talk about this thing called we're talking about this problem called a browser cache. So we might not have time to implement exactly like what we need to, but I'll post the full solutions afterwards, as always. So when you're browsing the internet, you have a cache of stored web pages that you visit a lot, right? And these caches are like finite in size. Otherwise, you just cache every web page you've ever visited and you just be able to access it just like that. So what happens when you run out of space in your cache, right? Just to be clear, this cache is saying like, okay, if I want to go to like this URL, I know that there's going to be like this data on this page. So in a lot of ways, you can think of it almost like sort of a hash map between like the key of the URL and the data of like whatever's on that page. So going back to the question of what happens when it's full though, one thing that computer scientists have agreed upon is that the least recently used algorithm is a pretty good way of keeping your cache clean. That is, when your cache runs out of space, you take a look at which page in your cache was least recently visited and you boot it out to make room for the new page. If you revisit a page that's already inside your cache, then you move that page to the most recently visited position, and it sort of like gets saved until, you know, it either hits the end of that queue or it gets visited again before that happens. So if you want more information on that, you can go to the link over there. But for now, let's worry more about how we might want to implement this. So say that I have a constructor that takes in an int as the maximum size of your cache. Because remember, like these caches do have to be finite in size, right? And you have a function that is you have just one function. It's just called getHTML. And that just returns a web page as an HTML string at a certain URL. You should optimize this for time complexity, which means that you should minimize the number of calls to this other function called findOnline. The reason why is because, yeah, you could go online like every single time if you wanted to, but again, the point of this is if you have slow internet, you'd be able to get the page as quickly as humanly possible. So given that, how might you be able to implement this least recently used queue? I think that it might be somewhat tempting to use like a regular queue at first. But a regular queue, at least in the way that like Java defines it, I don't know about other languages, doesn't really have too much in terms of functionality of like, oh, I want to like remove this element and then place it like back at the head. And even if it did, as an interviewer, I'd be like, nah, that's like not what I really want. So how can we sort of fix for that? I think that a doubly linked list would work very well in this case, right? And if you think about it, why would a doubly linked list work so well? You can implement a regular queue as a doubly linked list, as we've already shown. But in addition to that, you can also have methods that basically say, wait, I want to like take this item right here and move it to the head. Or you can say, as we already seen, I want to remove stuff that's like at the tail. So how can we sort of optimize this further? We've already seen that we can go through and just say, okay, well, I'm going to look through this cache by checking every element and seeing like what the eventual web page is. I think that an initial idea would be to say, wait, why not just use a hash map, right? But the problem is the hash map, like you would need to check for the oldest item inside the hash map. And that's an O of n thing, because presumably your hash map isn't sorted. If you had something like, I don't know if like a tree map's a thing or something like that, you might be able to lower that time complexity, but it's never going to be like O of 1 time to know what is the oldest item in a hash map at any given point. It's sort of like the problem that we saw last week, right, with a max stack. It's like, well, what happens when you remove the oldest one? How do you know what the next oldest one is? You sort of have to recheck through everything inside your map. So a pure hash map won't work because it's O of 1 to find the oldest element. A pure linked list won't work either because even though it's O of 1 to find the last element, it's still O of n to see if your URL is actually in the cache. How can you sort of combine these to get O of 1 for both of these?
So you want O of 1 adding and getting.
Yeah.
Right? So you could, I mean, if you have a hash map, right, and you, once it's out of the range of the queue, you can remove its key in the hash map, so you know it's you immediately know that it's not there if it's out. And if you can go back to the beginning of the queue, then that solves a lot of your problems. If you done the link less.
Yeah.
Yeah, so that's true.
So what are you mapping exactly in this hash map?
Oh, so it'll be mapped from HTML to string URL.
From HTML to string URL. Where does...
Or URL to actual...
Okay, yeah, so I think this still runs into the same problem that we were talking about before of like, wait, how do we know what the oldest one is though? Like we'd remove it from the queue and then we'd be like, okay, let's oh wait, you're saying let's remove it from the queue.
Yeah.
We take a look at what the URL is from there.
Yeah.
And then you take a look at the hash map and you'd say, let's kick that out as well. So
still runs into some problems.
yeah, so I think that a slightly different implementation might be to have a hash map of like your string URL to an actual node inside your queue, right? And I think that might be easier, especially because a special property of a doubly linked list node is that it can remove itself from a list with no reference to anything else, right? Because you already know what's like around you, so you can just cross yourself out, link those two, and that way you can exactly go and just remove yourself whenever necessary. So I believe that we can actually finish this up in the next 5 minutes. We already have almost everything that we need, especially because we already wrote this linked list queue, right? So let's copy this and just rename it to instead be a LRU cache. All right, so just like before, we had a dummy head and a dummy tail, and we initialized that, except we're also going to take in a size. And we're going to say int max size equals size, and I'm going to have an int size over here, and size is 0. Int size, I'm going to say this dot size is 0. Okay, cool. So at this point, what do we have with remove, right? So instead of removing, we would say remove, and let's give it an argument of a specific node to remove, right? So then instead of this node to remove being over here, let's keep the naming consistent so that way we don't even have to deal with that. So node prev is that, and node next is to remove dot next. So to remove next and prev are null. Dummy tails prev. In this case, it would be next, prev is prev, and prev's next is next. And we wouldn't need to return anything. We'll just be fine over there. So then we mentioned that we had a hash map too, right? Let's think about what it means to add. So adding is just really adding to head, right? So let's rename this add to head. And when we add something to the head, we would do... That's exactly the same thing as we had before, right? A new node, you create a new node with a value, you say a node's next is that, and then you create those new connections. So that's fine. Let's create something called remove to tail. Public void. Let's change this to a void. Public void remove from tail as just remove dummy tail dot prev. So that seems like it's pretty valid, right? Let's make a check for is empty. Just to make sure we don't accidentally remove dummy head itself in the case that it would be dummy tail.prev over there. So, okay. Cool. What else do we have, right? So after that, we have a move to head function, right? For if we see something in the middle and we're like, whoa, wait, we need to give it a second chance. For all of these, let's first say that size increases or size decreases and size increases. And for all of these, let's now finally define our hash map. So you have a map of strings to nodes. I'm just going to call it a map. And map is the hash map of the exact same. Let's import Java util. And over here, instead of a public node with like one int val, we need a string URL and a string data, right? So we have string URL, string data, instead of just one int val. And we'd say this.url is URL, this.data is data. Cool. Okay, so after all of this, let's go over here and just have dummy head as null, null, dummy tail is null, null. Okay, cool. So over here, let's take a look at what are some other functions that we would need to have, right? So what about a move to head? Add to head string URL, string data, URL data. Okay, so whenever you remove something, you'd say hash map.remove, and key would be to remove URL. And over here, we would put in the key being the URL and the data and the value being the new node itself, right? Okay, so then what about a move to the head, right, of a node to move? Then in that case, it would just be a combination of a remove node and just adding that to the head. Okay, awesome. So after all of this, we still have to get to our main thing, the get HTML, right? So public string get HTML. So, okay, the last thing over here is this, right? Over here, we are adding to the head, but we're never saying like, yo, if we add to the head and it's too big, we need to like kick something out from the tail, right? So in that case, we need to say if size is greater than max size, you would remove from tail. And that's the way that we would always guarantee that we would never have more than like whatever the max number of items is in here. All right, so we have a bunch of methods, all of which we should make private because the only thing that should be made public is right over here, get HTML of a string URL. And we have this helper function that was also private. It's private string find online URL. And I just return like something, but I would put that sort of check over there so that way we're sure that we're only going online when we absolutely do need it, right? And so over here we have our get HTML function, which is basically like if this exists in our queue, we're good. If what's it called? Our map contains the URL, then return map.get URL.data. Awesome, right? Else, okay. Otherwise, you need to say, okay, I'm gonna find it online. So string data is find online URL, and we would then add it to the queue. So add to head URL data. So that seems to work, right? Let's test this out with our own custom sequence of like whatever's inside, right? So how about let's say that we have an LRU cache that's of size like 1. And over here, we would say let's get q.get HTML A. It could literally be any string, right? q.get HTML B. And if the size is 2, then what we can say is if we try to get q.html C and then try to get A again, A is going to come, A is not going to be in a queue anymore. But if we did A, B, C, and then A, then the queue would be A and C. So if we tried to get C again at this point, it should be silenced. So at this point, we should do, you need to go online to find plus URL, right? Okay, so let's see if this makes sense. That's not, okay. Public string HTML, return data. Okay, and let's build this. So you need to go online to find A, B, and C. You need to go online to find A. You did not need to go online to find C. So obviously there's a lot more testing that can and needs to be done on this. For the interest of time, we're going to stop right here. But if you have any more questions, then let me know. We'll see you next week when Gung teaches trees. Thanks, everyone.